Welcome back to the Working Thesis. Today, we are talking about a ghost in the machine. And I mean that literally. Think about the hardware that runs the modern world. NVIDIA's GPUs training massive language models, Google's TPUs running search, Apple's silicon inside the phone in your pocket, Amazon's data centers. What if I told you that every single one of those advanced chips, all of them, is designed using software from essentially two companies most people outside of the hardware industry have never even heard of?
It is wild to think about. We spend all this time analyzing the trillion-dollar mega caps, the companies fighting for AI supremacy. But behind the curtain, there's this absolute bottleneck. The bigger of these two invisible giants is Synopsys, and they represent what might be the most unavoidable business in all of tech.
The premise for today's episode is that this software forms a moat so incredibly deep that even nation-states with functionally unlimited money and total motivation cannot easily copy it.
And that is exactly what we're going to unpack. We're going to look at what this software actually is, why the barrier to entry is so punishingly high, and why this business acts as a toll booth on the entire semiconductor industry. First, a quick and honest word. Everything you're about to hear is really just the two of us thinking out loud. Personal market commentary, made for learning and for fun. It isn't investment advice, and it isn't a recommendation.
And when we talk about a specific company, it's only ever to make a bigger idea click, never a nudge to buy or to sell. So take it as a starting point for your own curiosity. Do your own research and make the call that's right for you.
I have to admit, when we first started looking into Synopsys and the EDA market, my initial reaction was pure skepticism. I come from a software engineering background, and in the software world, we have a deeply ingrained intuition. Code is just code. If a product is just software, it eventually gets disrupted.
Right, the Silicon Valley ethos. Someone in a garage will figure out a way to do it cheaper, faster, and better.
Exactly. My gut reaction was, give a sharp team of engineers a couple of years, hand them modern AI tools to accelerate their coding, and they would rebuild this from scratch. How hard can it be?
Well, this entire episode is the story of why that intuition is totally wrong. We are going to walk through what actually stops that theoretical sharp startup in their tracks. Because the moat here isn't just about lines of code or clever algorithms.
It is about physics, manufacturing realities, and an ecosystem of trust that has been hardening for decades. To understand why you can't just code your way around this, you have to understand what it actually takes to draw a modern microchip.
Let's start with the basics. What is EDA? It stands for Electronic Design Automation. To understand why it exists, you have to picture the scale of a modern chip. A cutting-edge chip today has more than 100 billion transistors on a piece of silicon the size of a postage stamp.
And obviously, no human being is sitting there with a digital pencil laying out 100 billion tiny switches. You cannot do it by hand. You need software that designs, places, wires, verifies, and ultimately signs off on that chip before it is ever sent to a factory to be manufactured.
If you want an analogy, think of EDA as a combination of three things. First, it is CAD, computer-aided design for drawing the blueprint. Second, it is a spell checker, ensuring you didn't break fundamental rules of logic. And third, it is a crash test simulator, mathematically predicting how heat, electricity, and timing will behave in the real world before a single atom of silicon is etched.
That crash test simulator part is crucial. You aren't just designing a static floor plan. You are simulating the flow of electrons traveling at near light speed through microscopic wires, checking for interference, power leakage, and timing delays down to the picosecond.
Without EDA software, the modern semiconductor industry simply ceases to exist. You literally cannot make a chip without it.
So who actually makes this software? It is an incredibly concentrated market. Synopsys is the clear number one player. Cadence is a very close number two. And Siemens EDA, which used to be Mentor Graphics before Siemens bought them, sits in third.
Together, this big three controls the overwhelming majority of the market. By most tallies, they hold roughly 3/4 or more of the total EDA revenue. But if you look closely at the most critical, leading-edge tools, the absolute core of digital design, Some counts suggest Synopsys and Cadence alone approach 9/10 of the market.
It is a de facto duopoly at the leading edge. You have these two companies that essentially share the crown. They compete fiercely with each other, constantly leapfrogging on specific tool capabilities, but they basically shut everyone else out.
And this isn't a recent phenomenon. This concentration has been the reality for a long time. To understand how they got this locked in, we need to rewind a bit and look at where this all started.
Synopsys was founded in 1986 by Art Deguy, who is often called the father of logic synthesis. It was actually spun out of a research group at General Electric.
The breakthrough that launched the company was a product called Design Compiler. Before this, engineers had to do a lot of manual translation, but Design Compiler automated a massive leap. It took a human's high-level design intent, written in code called RTL, and automatically synthesized it into an optimized gate-level layout.
You wrote the logic of what you wanted the chip to do, and the software figured out how to wire the logic gates together to make it happen. That one leap in automation is what made the modern chip scaling era possible.
From there, the industry grew. Chips got exponentially more complex, and Synopsys and Cadence spent the next 30 years buying up every successful niche tool, rolling them up into these massive, comprehensive software suites.
This brings us back to my skeptic's question. Why can't a new startup just write a better version of Design Compiler today? This is where we hit the first real wall, the golden flow.
When you design a chip, you're targeting a specific manufacturing process at a foundry, like TSMC or Samsung. Let's say you are building for TSMC's N2 node, or their upcoming A16 node. The foundry has incredibly specific physical rules for how transistors can be placed and wired at that microscopic level.
To communicate those rules, the foundry releases a PDK, a process design kit. But they don't just throw the PDK over the wall. Foundries co-develop and certify their design rules and reference flows directly with Synopsys and Cadence.
TSMC essentially only guarantees that your chip will actually work and that it will yield a profitable number of working chips per silicon wafer if you used a certified flow.
This is the killer for a startup. A new tool has to be qualified on every node by every foundry. It is a multi-year, foundry-gated gauntlet. A startup could write brilliant code, but without the foundry certification, it is completely useless to a chip designer. It is a trust and liability barrier, not a coding one.
Which perfectly sets up the second layer of the moat, the catastrophic cost of failure. Let's look at the economics of manufacturing at the leading edge.
Doing a single advanced node tapeout, which is the moment you hand your final design over to the foundry to create the mask set, runs into the tens of millions of dollars, just for the masks.
And if there is a mistake in your design, a routing error, a timing violation that your software missed,
you have to do a respin. You lose months of time going back to the drawing board. You miss your market window, and you burn another multi-million-dollar pile of cash to make a new mask set. It is a financial disaster.
So ask yourself, is any project manager at NVIDIA or Apple going to risk a 9-figure failure just to save a few $100,000 on a cheaper, unproven software license?
Never. Customers gladly pay for the proven, supported, fully insured flow. It is the classic, nobody ever got fired for buying IBM effect, but on steroids with 9-figure stakes. The EDA tool cost is a rounding error compared to the cost of a ruined tapeout.
The third layer of the moat is time. EDA isn't just one app. It is hundreds of interlocking tools covering synthesis, place and route, timing sign-off, power sign-off, and verification.
Each of those tools embeds decades of brutal optimization math. They have encountered and solved millions of bizarre edge cases over 40 years of chip design. You simply cannot AI generate 40 years of silicon-validated trust overnight.
There is also the IP block business. Synopsys doesn't just sell tools. They sell pre-designed chunks of silicon logic. If you need a USB interface, a PCIe controller, DDR memory controllers, or SerDes for data transfer, you don't design it from scratch. You license it from Synopsys.
And those blocks are valuable precisely because they have already worked in real silicon 1,000 times. The payoff of this moat is incredible. Even companies like Apple and NVIDIA, who have massive engineering resources and do build niche internal tools for specific secret sauces, still buy the full commercial EDA flow. The tool is cheap next to the value provided, and building your own just hits the exact same certification and trust wall.
If you want the ultimate stress test of this moat, you just have to look at geopolitics.
Right. The US government recognized that EDA is a choke point. In the 2020s, and heavily culminating around 2025, the US moved to tightly restrict these tools to China. It has been an on and off policy, but the threat of being cut off forced China to act.
China threw its full weight at creating domestic replacements. They funded companies like Empyrean and Primarius. They deployed state capital, recruited top engineers, and had total existential motivation to break the duopoly.
And what is the result by 2026? Despite unlimited resources and motivation, domestic self-sufficiency in EDA is only around 10%. It is rising, but it is a massive uphill battle.
The domestic tools are workable, mainly at 14 nanometer and older, mature nodes. For the cutting edge, they are still years away. The Western trio still holds the large majority of even China's own internal market today.
To me, this was the absolute proof. If the world's #2 economy cannot copy this software under maximum pressure, that tells you everything you need to know about how deep this moat runs. It is important to balance this. China is making real progress at mature nodes and through novel 3D packaging approaches, so it is a serious long-term project. But it is absolutely not a near-term replacement.
Let's pivot to the business model, because the financials reflect the strength of that moat. Synopsys is essentially a toll booth on the entire semiconductor industry.
The revenue quality is spectacular. More than 90% of their revenue is recurring, driven by subscriptions and time-based licenses. They sit on a massive multi-year backlog, which makes their top line incredibly predictable and sticky.
And the profitability matches. Gross margins are consistently on the order of 80+%. Normalized operating margins hover around 30%.
They are insulated from the wild cyclical swings of chip sales. Whether NVIDIA wins the AI accelerator race, or Google's custom TPU wins, or a new startup takes the crown, Synopsys gets paid. Every single player designing a chip has to pay the toll.
We have to talk about AI, because in the EDA world, AI is acting as a massive double tailwind.
First, AI is driving more customers. We are seeing a total explosion in custom silicon. It isn't just Intel and AMD anymore. Google has the TPU, Amazon has Trainium, Microsoft built Maya, Meta has MTIA. Automotive companies are designing custom chips.
More companies designing chips means more engineers needing EDA seats. It dramatically expands their customer base. But the second tailwind is AI inside the tools themselves.
Exactly. Synopsys has a product called DSO.ai, and Cadence has Cerebrus. These tools use reinforcement learning to explore the design space and place components much faster and more efficiently than a human engineer could.
And here's the kicker. The incumbents own the one thing an AI-native startup lacks: decades of real-world, silicon-validated design data to train on. They are the arms dealers for the AI era. Whoever wins the AI hardware war, the EDA duopoly sells the weapons to all of them. AI isn't a threat of a slowdown here. It is an accelerant.
The nature of chips is also physically changing, which drove Synopsys to make a massive strategic move. Historically, chips were a flat, 2D layout. Now we are moving to 3D stacking, chiplets, and co-packaging silicon directly with optics.
When you stack chips on top of each other, the problems change. You have to rigorously simulate the physics. You have to account for thermal dynamics, heat trapping, electromagnetic interference, and mechanical stress. Logic simulation is no longer enough.
Which is why Synopsys closed its roughly $35 billion acquisition of Ansys, the clear leader in multi-physics simulation, in mid-2025. It was a huge swing, first announced back in early 2024, and now they are actively integrating it.
It represents a shift from just chip design to silicon to systems. By bringing Ansys in-house, Synopsys expands its addressable market from roughly $18 billion toward $30 billion plus. They want to simulate the entire system, from the transistor up to the cooling fan on the server rack.
But we have to look at the other side of the ledger. If this is the perfect business, why did the stock fall about 40% from its 2025 high?
It has been a genuinely rough patch for execution. In late 2025, they delivered a rare earnings miss and had to lower guidance. Part of that was the geopolitical reality catching up. The China export restrictions finally took a real bite out of their IP block business.
Then there is the reality of digesting Ansys. A $35 billion acquisition brings significant debt, dilution for shareholders, and massive integration headaches. They actually announced roughly a 10% workforce reduction to rationalize costs. They have self-described 2026 as a transition year.
The market reacted violently. Synopsys historically traded at a rich premium. We saw that multiple reset sharply, by some measures compressing from the mid-50s times earnings down toward the high 20s.
It is a classic case of an unbroken moat running into very real, very difficult near-term execution hurdles. The competitive advantage is fully intact, but navigating a transition year while digesting a massive acquisition is genuinely harder than the smooth sailing they enjoyed a few years ago.
So, bringing it all back to where we started, how is the skeptical software engineer feeling about this moat now?
Fully converted. When you understand what EDA actually is, you realize it is a wide moat duopoly acting as a toll booth on the entire AI chip era.
It is protected by foundry certification, the catastrophic cost of failure for customers, and 40 years of silicon-proven trust. And as the China experiment proves, money and motivation alone cannot break it.
Even as they work through a self-inflicted transition year with the Ansys integration, the core reality remains. This isn't just software you can replicate in a weekend hackathon. It is the invisible infrastructure that the modern world is built on.
Thanks for joining us on this deep dive into the invisible toll booth. See you on the next episode of The Working Thesis.
And that's where we'll leave it for today. Thank you, genuinely, for spending part of your day thinking this through with us.
The whole idea of this show is pretty simple. We hold a handful of theses about the world, and we test them out loud, together, a little more each day. No crystal balls, just curiosity, and a willingness to be wrong.
So, if that's your kind of thing, stick around for the next one, and tell us where we're getting it wrong. Honestly, the pushback is our favorite part.
Until next time, take care of yourself, and keep asking good questions.